All right, so I'm going to break 9/6 into two separate videos. I would highly recommend watching the video on example 2 before you watch this one. We're going to talk about writing the equation of sine and cosine curves in example 2, and we're going to use some of that stuff in examples 1, 3, and 4. So I would come back to this one after you've watched the other one. But we're looking at sine, cosine, or just periodic functions in real life. So oftentimes we can use sine and cosine functions or trig functions in general to represent things like sound waves, motion of pendulums, or seasons of the year, something that reoccurs like on a set interval. And the one thing I want you guys to know before we get into the first example is the last thing I underlined here. The reciprocal of the period is called the frequency. So we don't want to confuse that frequency with the frequency that we see when we're writing the equations of sine and cosine. But that's going to be something that we're going to note and then use as we get through the last couple of examples. So example 1 here, what we've got is we've got an audiometer that produces pure tones to test a person's auditory functions. So an audiometer produces a pure tone with a frequency of 2000 hertz. So this is our frequency, this frequency up here, not the frequency that we necessarily use in our trig equation. So what that comes down to is 2000 cycles per second. Okay, so hertz is cycles per second. The maximum pressure produced from the pure tone is 2 millipascals. So that's something we're going to underline as well. Maximum pressure, 2 millipascals. So that is somehow going to relate to that amplitude that we put into our equations. We want to write and graph a sine model. So sine, not cosine, that gives the pressure P as a function of time. Okay, so a couple of things that we need to know. The first thing I'm going to do is I'm going to write the standard equation for sine. It looks like this, where A is that amplitude, gives us max and min values, sort of, depending on the sinusoidal axis shift. B is our frequency, H is the phase shift moving left and right, and K is what happens when our graph moves up and down. Let's fill out what we do know. Now, I know that we have a maximum pressure of 2 millipascals, so our amplitude then is 2. I'm going to rewrite this as P in terms of T instead of Y. A function of P in terms of T, where A, our amplitude then is 2, comes from that maximum value that we're given. We know that this is a sine function, so last we need to find that frequency. We need to find the value of B. So given the information from the top there, the reciprocal of the period is called the frequency. So we're told here that the frequency is 2000 hertz. Okay, which is 2000 cycles per second. We are also told from the top that the reciprocal of the period is the frequency. So the period then of this function is just that reciprocal, 1 over 2000. Okay, so we can find the frequency of our function, which I'm going to call B because that's what's denoted in the standard equation for sine. That is always our standard period for sine or cosine, 2 pi, divided by the period. That becomes 4,000 pi radians. That's going to go into our equation here where we would put the frequency. I'm going to switch the variable to t since we're measuring in time. And then we're not given any information about any other shifts. So that is our final equation here. 2 sine 4,000 pi t. And the last thing we're asked to do is just sketch this. So because we're measuring the x-axis in seconds or in time, I'm not going to worry about plotting points to the left of the y-axis. We don't measure time in negative values. I need to make sure that I also include the minimum and maximum values that come from that amplitude. And then the last thing I need to do is figure out how to scale this along the x-axis before I plot the points for sine. So our period is 1 over 2000, which means that our subinterval is 1 over 2000 divided by 4. So it's 1 over 8,000 for our subinterval length. So 1 over 8,000, 2 over 8,000, 3 over 8,000, 4 over 8,000. And then we're left to just plot the sine curve. So sine always starts on the sinusoidal axis, goes up to its maximum axis, minimum axis. And that's where we land with that sine curve I'm going to go through that last point because we know sine repeats for x goes to positive and negative infinity. We only care about the right side of the y-axis because we don't measure time in negative seconds. Okay, so that's example 1. We are going to example 3. Okay, we got 2 people swinging jump ropes. We are told that the highest point of each jump rope is 75 inches above the ground, and the lowest point is 3 inches. So these 2 ropes do not touch the ground. The rope makes 2 revolutions per second. That's going to be really important information. I'm going to also underline 75 and 3. We want to write a model for the height in inches of the rope as a function of the time t in seconds, given that the rope is at its lowest point when t is equal to 0. So that is actually a really tricky way of telling us what type of trig function we're using. When the rope is at its lowest point when t is equal to 0. So we'll come back to that. But we are asked to essentially write either sine or cosine. We're not told which one. So that's the first thing we're going to start with, is figuring out what we're using here. Okay, so if you guys go back to the core concept on the note packet right before example 2, there are 4 graphs at the bottom: positive cosine, positive sine, negative sine. We are told in that last sentence, the rope is at its lowest point when time is equal to 0. So look at those 4 graphs on that core concept box and see which of those graphs starts at a minimum on the y-axis. When t is equal to 0, when x is equal to 0, which of those 4 curves is starting at a minimum? That is negative cosine. So this last sentence tells us we are using cosine, and it is the reflection of cosine. It is actually negative cosine. Okay, now that we've got the function, we've got to start figuring out what all of the rest of the values are going to be. So let's start with that amplitude. To find the amplitude, we've got kind of a shift going on here. We have a maximum, we have a minimum value. In order to find the amplitude, we take the max, subtract the min, divide by 2. So 75 is the maximum height, 3 is the minimum height. We are looking at an amplitude then of 36. Okay, from that we can find the sinusoidal shift, okay, or the vertical shift up or down. That is just going to come from taking the maximum minus the amplitude. Which is 39. All right, so our sinusoidal axis there is 39. You could also take the minimum and add the amplitude. You get the same value, and that should be the same every single time. All right, last thing we need is that phase shift, or excuse me, the frequency. So B, the value of B. Okay, here's what we were told. I underlined it. 2 revolutions per second. The rope makes 2 revolutions per second. So we can infer that we make 1 revolution in 0.5 seconds. So that is our period. Our period is 0.5 seconds. 1 revolution happens in 0.5 seconds. That becomes the period. So the frequency then is just 2 pi divided by the period. So we are looking at 4 pi for our frequency. All right, put it all together. The height of the jump rope in terms of time is equal to negative 36. That's our amplitude. The negative cosine of our frequency, 4 pi t, and then the sinusoidal axis shift up 39. That is the final answer. Give that what if a try with those changes. See if you guys can come up with the answer. Check your answer online. The last one I'm going to do with you guys is example 4, and you need a graphing calculator for this one. Okay, so we have this table, shows the number of hours of daylight in Denver on the 15th day of each month, where t is equal to 1, representing January. We want to write a model that gives n as a function of t, and then we'll interpret the period. We'll talk about the period later. So we've got this table of values 1 through 12 because there are 12 months of the year. We are going to type this into a graphing calculator and use it to get some sort of regression. So just a brief review with the calculator, and then I'll go in and finish the points. If you guys hit stat, we're going to go to edit, and we're going to type in 1, 2, all the way to 12 here, and then you'll go over in list 2, you'll type in the numbers underneath. I'll be right back. Okay, I've got everything input in the list, and now we are going to go into the calculator, and we're going to just use it to generate an equation. So if you forgot, you're hitting stat, you're going to go over with the arrow key to the right to calculate, and then what we're looking for now is sinusoidal regression. So option C, if you've got a TI-84, hit enter, and then go down to calculate. Now, we want to pay really close attention to how the calculator is telling us we write this equation. We are going to write the frequency inside the parentheses, so that's kind of the only difference there. All right, so what are we told? Y is equal to 2.76 all around to the nearest hundredths place times the sine of B, which is 0.51x plus C, in this case C is negative, so minus 1.59, and then on the outside plus D, 12.13. Okay, that's our equation using our calculator. Calculator is only going to give us sine equations when we use a sinusoidal regression, because sine and cosine are just phase shifts of one another. It just keeps that into account and just generates a sine curve. The last thing we're asked to do is interpret the period of this graph. Let's talk about the period. So we've got this frequency here. Our frequency is 0.51. So the period is standard period of sine, 2 pi, divided by that frequency, 0.51. That is about 12 if you calculate that in your calculator. This makes sense because we're talking about the number of hours of daylight every month. There are 12 months in a year, and we would expect after 12 months for the cycle to start repeating. We should have roughly the same amount of daylight in June of 2019 as we have in June of 2020. Okay, so that is how we can apply the writing of equations in real life. Example 2 is done on a separate video. Email me if you've got questions.